Welcome. Let's talk about the efficiency of the async runtime in Rust known as Tokio. After this talk, you may want to reconfigure your apps. You'll certainly want to evaluate and measure the performance of your apps. Let's start off by comparing Rust to Node.js. On the test machine, we have 12 cores, so we are going to get 12 threads by default in the Tokio runtime. The results that you're about to see are going to be impacted by how many CPU cores your machine has available, whether or not you're running in a Docker container, and ultimately how many CPU cores are reported by the API that Tokio is using to determine that count. We will start with this web frameworks project, which you can see is from this location, the benchmarker web frameworks. And we're just going to test Rust against Rust. So we'll start by using the default for OHA, which is a web test framework. And we'll also use the default for Warp, which is the server we're going to be testing, which is written in Rust. So we're going to send 10 sockets of concurrent requests. It's 120K RPS. We're going to take a look at CPU usage here, about 250% for OHA and 210% for Warp. And we hit an RPS rate of 117,000 requests per second. Now let's change that. Let's go with one thread for Tokio for the client, and we'll leave the server app at the default of 12 threads. So now we're going to see it's a little bit slower. The server is using 114% and OHA is using only 100%. We're going to take a look at these stats on the board in a moment, but if we go and drop the server to one thread and test that using the client at one thread, see the RPS rate's a little bit higher, and both are using under one CPU. Now let's set OHA to 2 cores, or 2 threads. If we do that, we're going to end up right around 100K RPS. And we're using about 129 for OHA and about 100 for Warp. Now let's look at what Node.js can do with just echoing a response from OHA. So we're going to go directly to Node.js, and Node is going to hit about 114%. It's got a single thread for JavaScript, and OHA is at 30% CPU. It's limited to about 20 to 21K RPS. Now, if we pass through a framework I've written called Lambda Dispatch, we're going to pass through port 5001. We're going to hit the Rust-based extension, which is using the current thread runtime. Actually, let's stop that and let's use the default multi-threaded Tokio runtime. So that's going to create the 12 threads. Our router is written in .NET. That's not particularly relevant at the moment. So we're going to test this with OHA at 2 threads. We're going to hit 15K RPS, but the extension is at almost 300% CPU to hit 15K RPS. That is a lot. Now, let's stop the extension and let's switch it to the current thread runtime. I have code that monitors this Lambda Dispatch variable and reconfigures which runtime it's using in Tokio. So now we're going to test it, and we're going to see that the throughput should go higher, 17K RPS, up to 18K. Without Camtasia running, it's going to hit 20K RPS. But you see the extension is only using 92% CPU. So the CPU usage of the extension is dropping to almost 30% of what it was with the default of 12 threads, yet the RPS rate has increased 20 to 30%. Okay, so in conclusion, I think there's an issue. If you know the answer, post it in the comments below. But with Tokio, if you're allowing it to use far too many threads than you actually have CPUs for and that you have work for, you're going to have a lot of additional CPU usage. I don't know what it's from. I have tried some custom local builds of the Tokio runtime. All of Go, .NET, and Rust use work stealing algorithms for their async runtimes. And I've tried to make some adjustments to that. It hasn't had an effect yet. I'm still looking for some possible fixes. But ultimately, all 12 threads end up being busy when you allow it to use 12 threads, even though, as we've shown, there's actually less than one thread worth of work. It does increase the context switching substantially. This is a well-known problem in computer science. There are lots of papers on it. The solution isn't going to be trivial, I don't believe, but you may want to reconsider for your Rust apps or even your .NET apps, possibly your Go apps too, whether or not you really truly want to be using more than one thread and more than one core per process. If you split these up and have each process independently handling only a single thread, I believe you're going to retain the efficiency that you get with a single thread. So give it a try. Reduce your thread count. See if your throughput goes up and your CPU usage goes down dramatically.
All right, this is the table of results we get with the OHA Rust client and the Warp Rust server with different configurations of the number of threads for the Tokio Async Runtime. The default on an M2 Max with 12 cores is to run 12 threads for both. We observe 120,000 requests per second. We get 56,000 requests per second per core. We use 215% CPU. The client with the same 12 threads is getting 48,000 requests per second per core and is using 250% CPU. If we cut them both to one thread, we go up to 127,000 requests per second per core on the server and 108,000 requests per second per core on the client, both of which are more than 2 times more efficient than the default case with 12 threads. You can see the other cases here. If we allow the client to go to 2 threads, it becomes a little less efficient, but we are able to max out the throughput of the Warp server, hitting 126,000 requests per second at 128,000 requests per second per core. You notice this grows linearly. So we stay at one thread, we increase the throughput. We do not use substantially more CPU for those additional requests. We just end up hitting the max at 100% of one core. That's it. There are other runtimes that have the same problem, and I'm going to cover those in a different video. Thanks.